Hi everyone, welcome back to Prieto TV and welcome back to Prietology. If you're wondering why I'm dressed like this, it's because I had a formal attending to go to today, so yeah, that's why. Today's episode is episode 3, it's called Doing the Wave. Like I said last time, we'll just be doing waves, so talking about frequency, amplitude, and hopefully the electromagnetic spectrum. So, let's start reviewing our key terms. Alright, so our key terms today is water wave. I'll get into why we're doing water waves. Sound, frequency, amplitude, analog, digital, and the electromagnetic spectrum. So, let's get started. Okay, so our first term is water wave. Water wave, it's kind of like a fundamental idea or thing to get a good type of understanding for a wave. So a wave is a type of energy. So if you think of water waves, they're like this, they flow like that, and so they are a wave. And also water waves are a type of energy. They are kinetic energy. Waves are energy that travel from point A to point B. So one point to another point. So these are usually related to frequency and amplitude. So frequency and amplitude are varying variables between a wave, and waves don't have a specific measurement. They have little different components and parts of it that have specific measurement. So the more energy a wave carries, then it's going to have higher peaks. So water waves are made by moon's gravity. So the moon's gravity pulls on the oceans and then makes the waves. If you're wondering why it doesn't have it on rocks, probably because there's like a stiffer platform because water is more wavy. Fun fact, the height of some killer waves like giant tsunami waves can be up to 15 meters or 49 feet. Alright, so our second term is sound. Sound is a type of energy that can be detected by your eardrum, so they are waves. These are usually measured in decibels with a lowercase d, capital B, so with a small d and a big B. They are longitudinal waves, which means they are waves that are from vibrations and matter. So if I do this, that creates sound. So me hitting this, the energy transfers from it, knocks the matter around the air, and then comes into the camera microphone, and you hear that as sound. These waves cannot travel in vacuum because there's nothing to travel with. There's no matter in vacuum, so you don't hear anything in space. So breaking the sound barrier is going faster than the speed of sound, which is known as a sonic boom. Fun fact, the speed of sound is 300 meters per second, not as fast as light, which is 300,000 kilometers per second. Alright, so our third term is frequency. Frequency is the amount of repeating wave patterns, so the amount of waves in one wave, so the bumps and hills, which are called crests and troughs, so peaks and troughs. Peaks is the high part, troughs is the low part. So the amount of peaks and troughs per unit of time, so hours, minutes, seconds, milliseconds, whatever you want, but it has to be time. This is usually measured in hertz, not this. Ew. Hertz. It's measured in hertz like Hz, which is H-E-R-T-Z, hertz. This is related to pitch and energy of different spectrums. So like pitch, the different frequency can affect pitch, which is how something sounds. Higher frequency means there's more peaks and troughs in a wave. So like I said, it's more compact together, so there's a higher frequency. And usually this means there's a more amount of energy carried in a period of time. So fun fact, the household electricity frequency, because sometimes frequencies can be measured on like those wave graphs like this, they are usually around 50 hertz, so 50 hertz per some unit of time. Alright, so our fourth term is amplitude. Amplitude is a property of all waves, and this is measured in meters. As we know, meters is a lowercase m, and it's a height unit. So the more amplitude a wave has, the more energy it carries. What's amplitude, you ask? Amplitude is the height of the crest or peak in a wave. So if you think of a wave like this, the high part, that's the crest. The height between the middle part of the wave, so if a wave moves like this, the middle part of the wave to the highest point is the amplitude. So more amplitude, more energy, and this usually measures a wave's movement. So amplitude is used in AM radios. So the first AM radio transmission, fun fact, was in 1906. So AM radios have been around for more than 400 years. Alright, so our fifth term is analog. Analog is a way to send information using carrier waves. This is usually used in radio and TV broadcasts, so this is more of an old-time technique of sending information. This usually, like I said, transmits information using carrier waves, like radio waves. So radio waves are carrier waves, or electric currents. We'll get into electric currents at the end. That is actually our last episode, electricity and magnetism. So new modulated waves that come from analog waves have the same peaks and troughs as the original. So you send information, it has the same peaks and troughs when it comes back. Fun fact, the first phone call using analog carrier waves was made by Antonio Meucci in 1854. Alright, so our sixth term is digital. Digital is a very sleek and modern thing. It's noise free, so you don't hear that staticky noise. And it's quick and it's easy. Instead of using carrier waves, it uses binary, ones and zeros, which mean either off or on. The one meaning on and the zero meaning off. If you ever look on a lamp, let me see if I can find one really quick. Couldn't find anything. So what I mean by going on and off, if you see on those those lamps that have a little switch and one has like a line and the other has a circle, that's binary. The one meaning on and the zero meaning off. This is usually used in CDs, DVDs, computers, TVs. It basically feeds our modern world. We've gone away from the analog place and we're ready to power our world with digital. So a fun fact is that these were used in the first computer, the Z3, which was made in 1941, probably for World War II. It's getting a little hot in here wearing this thick jacket here. Alright, so our final term is the electromagnetic spectrum. The electromagnetic spectrum is a list of all the waves that we've learned here. So we've learned about water waves, frequency, amplitude. We're taking all this and putting it into the electromagnetic spectrum, which is, like I said, is a list of all the waves in the universe. So the electromagnetic spectrum is a list of waves, like I said, of different frequencies that make up our spectrum of waves. They're all photons, which are little tiny particles the size of electrons. We'll learn about them later, that are different amounts of energy. So the order this goes is the lowest is radio waves, then microwave, infrared, light, ultraviolet, X-rays, then gamma rays. Light is the only visible light band. It's a very tiny band that we can see of radiation. Let me show you a picture of the electromagnetic spectrum. Alright, so here you see a picture from our experiment book. Right there at the end, those are the radio waves, then microwaves, infrared, visible light, ultraviolet, X-rays, and then gamma rays. If you can notice that the radio waves, they're farther apart from each other, each of the crests are farther apart, and in the gamma rays, they're very close to each other. This is something that's called the wavelength, the distance between each crest. So larger wavelength is lower energy. So that's why radio waves, they have the longest wavelength, therefore they have low energy. Gamma rays have low wavelength, therefore they have lots of energy, and gamma rays are very bad for you, so don't mess with them. Well, looks like we covered all our key terms for today, so let's get on to experiment of the day. Alright everyone, this is experiment of the day. It's called lenses and light. What you need, choose 2 sheets of cardstock. These are one of those little like folders, like those paper folders. I just cut one side to get some cardstock. A marker, we got one right here. 2 tall clear glasses with straight sides right here. They have a little green at the top, but I don't think that'll affect them. And some water. Alright, so for the procedure, you need to fold the first cardstock in half. So let me fold it in half. Let me put the logo on the inside so it doesn't disturb it. Fold this in half, and then so it can stand up. So now we have to draw an arrow on one of them pointing left. So let me draw one pointing left. There we go. We have our arrow cardstock pointing left. Let's put that over there. Now we need to take the other one and fold it in half as well. And now we have to draw an arrow pointing up. So let me draw an arrow. There we go. We have our arrow pointing up. So now we have to put the empty drinking glass in front of our arrow. Alright, let's do this arrow first. So we have our drinking glass here, if you can see it. We have our drinking glass there, and now we have the empty drinking glass in front of it. And if you look at it, The arrow is a little distorted, but the arrow is a little distorted. Actually, let me elevate the cup really quick so the arrow is more warped. Alright, so there you have the glass. And so now we put it in front of it. It looks like a little distorted sideways arrow. And now we put the thing in front of it, and now we pour water inside this one. Alright, the arrow should be somewhat distorted. Now the arrow, if you see, it's pointing the other way. Let me move the camera this way so you can see it. If you see over here, I don't know if you can see that well, but from here, looks like the arrow is pointing a different way. Let's see if you can see from over here. There you go, now you can see it better here. It's a little distorted, but you can see the arrow is pointing a different way now. It's pretty cool. Need to clean some things up really quick. The book got wet with water. Alright, so now we're going to take our second arrow pointing up, and then we're going to put the glass, empty glass in front of it. And if we look at our arrow, it looks a little distorted because the glass is not super clear, and it's still pointing up. But now, if we pour the water, let me pour the water off center so the book doesn't get wet again. We have our water here. Now if we put it in front, look at that. Let me see what it looks like here. The arrow almost looks like it's pointing down. It's a little distorted because this is not the clearest glass. Let me move it out a little more. It still kind of looks the same. Looks like the arrow still is pointing up. Interesting. Well, that was kind of a disappointment. I thought the experiment would be better. Well, the reason that the horizontal arrow kind of refracted a bit, is because the light bends around the glass. So the glass with the water, it's called a refractor because it refracts the light, which means it bends it a different way. So the glass, like I said, the glass bends the arrow, so the arrow's in a different form. The second arrow doesn't flip, so the arrow, this one, didn't flip because the glass only affects horizontal light. Well, I think that's all for today. So next video for Prietology, our topic is, we're gonna actually revisit an old topic from chemistry, atomic structure. We're going back to that, but we're gonna go even deeper. We only talked about the parts of atoms like protons and neutrons, but now we're gonna see what they're made of. We're gonna see what protons are made of, neutrons are made of, quarks, strong force, and we're even gonna go to antimatter, things that are so expensive to buy they almost feel like they're science fiction. So yeah, it's gonna be a pretty interesting episode next time, so stay tuned. Well, I guess this concludes episode 3, so thank you for watching, and if you like this video, leave a like and consider subscribing. See ya.